Now, three states of matter: solids, liquids, and gases, right? Now, in that solid, liquid, and gases, these three states, we are going to just differentiate between them. Solids, they have a definite shape and they have a definite volume. Liquids, they don't have a definite shape. In whichever container I put them, they get the shape of that particular container. And if I'm talking about gases, they don't have a definite volume nor do a definite shape. Wherever I put them, they are going to adjust themselves in that particular region, right? Okay. Now, what we are going to do is we are going to move a little bit further. Let me move on to my next slide. Right. Okay. Three states. And what about the intermolecular forces of attraction? Solids are very strong, and basically I'm interested in the gases. Gases have very weak intermolecular forces of attraction. Now, another thing that we are going to just go is we studied about the fundamental quantities and the 7 fundamental quantities, amount of substance. Now, the SI unit of the amount of substance is mole, right? And that particular SI unit amount, what is that 1 mole, right? 1 mole is nothing but the amount of substance that contains same number of atoms or molecules or particles or ions or electrons or whatever as there are in 12 grams of carbon 12. Now, we already know that why am I using carbon 12, because that is the very abundantly available carbon isotope, and it is a very stable thing, right? Okay. In between, I'm admitting people. So, right. Okay. Now, another thing that I want to talk about is the Avogadro's number. What is this Avogadro's number? It is 6.022 into 10 raised to 23. Now, what is that? That is a number. What is that number? That is the number of particles or atoms or molecules that are present in 1 mole of that particular substance. If I'm talking about gold, what is 1 mole of gold? 1 mole of gold is, if there are 6.022 into 10 raised to 23 atoms of gold present there, I call it as 1 mole of a substance, right? So that is the Avogadro's number. Now, what we are going to do is, I think all this you have done in your chemistry, right? And some part of it we have definitely done in physics, but this Avogadro's number you've used a lot, I think, in your chemistry. Now, let us actually move on to this particular chapter, right? Okay, let me move on to the next slide. Now, here I'm basically, somebody is drawing. I want people to stop doing that. Okay. Now, we are basically talking about 3 kinds of laws. One is the Boyle's law, the other is the Charles law, and the third is the Gay-Lussac's law. Now, whenever I'm talking about a gas, I'm talking about 3 quantities, that is the pressure, volume, and temperature. Now, we are going to relate these 3 quantities, and these are the 3 laws. What did Boyle have to say? That if the temperature remains constant, then the volume is inversely proportional to the pressure, right? Boyle's law says that volume is inversely proportional to the pressure if the temperature is remaining constant, right? Then what did Charles have to say? That the pressure, when the pressure is constant, then the volume is directly proportional to the temperature. When the pressure is constant, volume is directly proportional to the temperature, is what the Charles law says. Then the third law that we are going to talk about is the Gay-Lussac's law. Again, what we are going to do is we are going to keep the volume constant in this case. And what did Gay-Lussac have to say? That when the volume is constant, what is happening is, when the volume is constant, at that time the pressure is directly proportional to the temperature, right? All of you all know these 3 laws, right? Now, what we combine all these 3 laws, and we get into something called as an ideal gas equation. Now, 11th standard, you have done in chemistry what is an ideal gas and what is a real gas. We are going to talk about it, but later on, right? So we combine these 3 laws, and what I get is PV is proportional to the temperature, right? Or I put in PV is equal to nRT. Now, N and R are the proportionality constant. Now, what is N? N is the number of moles. Now, what is that number of moles? It is the mass of the gas, right? Divided by the molar mass. Now, what is molar mass? Molar mass is the mass that you're going to talk about in moles, right? Molar mass is the mass of that substance that you're going to talk in terms of moles. And this mass that I'm going to talk about, it is in terms of grams, kilograms, right? That is the mass of the gas. Now, if I take this, then I can, if one particle has a mass of m grams, right? Then I can, and there are n particles in that particular container, then what is the mass of the gas? It is n multiplied by m. What is n? N is the number of atoms or molecules or particles, whatever we say, of that particular substance multiplied by mass of one particular particle. If small m is the mass of one particular particle, then n multiplied by small m is going to give me this mass of the gas. Similarly, if I'm talking about a mole, right? If I'm talking about a mole of that gas, if m is the mass of that particular particle, right, then Na into small m will be the molar mass, right? Na into small m will be the molar mass. No problem if you don't remember right now. Again, we are going to get into this Na into small m. Na into small m is the molar mass, right? Okay. And this R is nothing but the universal gas constant. Its value is 8.314 per mole Kelvin, right? And it is same for all gases. That is why the name is universal gas constant. Okay, now what we are going to do is we are also going to talk about, instead of using this PV is equal to nRT, we are going to talk about some quantity PV is equal to N into Kb into T, right? Now this Kb is nothing but your Boltzmann constant. Now how did I get this Kb into picture? How did I get this Kb into picture? The universal gas constant is given by Na into Kb. Right? Universal gas constant is the Avogadro's number multiplied by the Boltzmann constant. Now this Boltzmann constant, I will talk about it a little bit later, right? This Boltzmann constant, we are going to get into it. It is nothing but your average kinetic energy of the particles related to the thermodynamic temperature. That particular constant, right? That particular proportionality factor that relates nothing but the average kinetic energy of the particle with thermodynamic temperature. Big words right now. Let us not get into the details. We'll again, when this Boltzmann constant comes into picture, we are going to talk about that Boltzmann constant, right? Now, how did I get this N into Kb? I know that small n is capital N, that is the number of molecules of that gas, divided by the Avogadro's number. So if instead of small n, I put N, capital N divided by Na, right? And the value of R is nothing but your, just let me admit people in between. Okay. Now R is nothing but your Avogadro's number into the Boltzmann constant, right? So if I put this Avogadro's number, that is Na into Kb, and this is N upon Na, Na and Na will get cancelled, and I will have the equation PV is equal to N into Kb into T. What is P? Pressure. V is the volume of the gas. P is the pressure of the gas. And the temperature at which I'm talking about this pressure and volume, that is capital T. N is the number of molecules, and Kb is your Boltzmann constant, right? I need this expression later on. Now I don't need this expression for the moment of time. Okay, let me move on to the next slide. Okay. Now here I'm talking about, we have an expression PV is equal to N into Kb into T. I'm just going to try and apply, right? Now there are two vessels are filled with same gas where the volume, temperature and pressure in the vessel A is twice the volume, temperature and pressure in the vessel B. Calculate the ratio of the number of molecules of gas in vessel A to that in vessel B. Now what they have said, that the volume of the gas in the vessel A is 2 times the volume in vessel B. Similarly with the temperature, similarly with the pressure. Now I have the expression PV is equal to N Kb into T. Now what is going to change? Kb is a Boltzmann constant, that is going to remain as it is. The value is not going to change because it is that particular ratio of proportionality constant for average kinetic energy to the with the thermodynamic temperature, right? Okay, so what we are going to do is, just let me admit people, please. Okay. Right. So P1 V1 is equal to N1 Kb as it is T1. P2 V2 is equal to N2 Kb T2, right? Now what we are going to do is we are going to take this ratio. If I take this ratio, I just reshuffle this. N1 I can write as P1 V1 upon Kb into T1, and N2 I can write as P2 V2 upon Kb into T2. This is what I can write. So when I put this, N1 by N2 is nothing but P1 V1 P2 upon P2 V2 into T2 by T1. If I put the values, everything is twice. Now this temperature T1 is in the denominator, right? T1 is in the denominator, so 2 times of T1 is going to be there in the 2 times of T2 is going to be there in the denominator. So if I put the value, I get the ratio as 2:1. Right? I get the ratio as 2:1. Let me move on to the next slide. This is the numerical from your textbook. Okay. Right. Now let us talk about the ideal gas and real gas. Right? Ideal gas, you know the word ideal. Ideal means hypothetical, ideal, very ideal kind of situation, that kind, right? That is not the reality. Now, what is that ideal gas? Ideal gas, we consider that the intermolecular interactions are absent. Now, why am I talking about all these intermolecular interactions are absent? Whenever I'm talking about a gas in a container, there are thousands and thousands of molecules inside that particular container. And I cannot possibly talk about one particular molecule. Whatever I have to do, I have to talk about that entire set of molecules, right? So this intermolecular forces of attraction become an important concept there. Right. So in an ideal gas, the intermolecular interactions are absent, right? And in a real gas molecule, the intermolecular forces of attraction are there, they are present, right? The force, we know that they are very, very small in comparison to your solids, right? The intermolecular forces are very, very, very small, but they are there, right? And in real gases, we consider that they are interacting with each other. And in an ideal gas, we are considering that they are absent, absolutely they are not available there. Now we don't have, no real gas, right, is truly ideal. No real gas is truly ideal. Now what we are going to do is, if I have, but at very low pressures, low pressure or very high temperature, the molecules are very, very far away from each other, and therefore those real molecules or real gas molecules have negligible molecular interactions, right? When does this happen? I'm talking about the pressure being very low, right? They are very far away from each other, temperature is very high, and in this particular case I can consider that the intermolecular forces of attraction is very, very small, right? Or it is negligible. And I can consider under these conditions that real gas is nothing but your ideal gas, right? Real gas is going to behave like an ideal gas. Whatever expression we have, PV is equal to nRT, is actually the expression for an ideal gas, right? Now let me come to this particular diagram. I told you that there are thousands and thousands of molecules in that container, and these molecules, all of you all know, 11th standard chemistry, they're not stationary. They are in random motion, what we call as the Brownian motion. They are continuously in random motion, Brownian motion, right? Now, when they are in Brownian motion, they are moving at random, and when they are moving at random, they are going and colliding with particles here and there, right? They're going and colliding with particles, with various particles, they're going and colliding. And when they for example, let me talk about this particular molecule. This molecule travels this particular line, collides with a molecule that is here. And when it collides, obviously the direction is going to not remain the same. Let us talk about an accident, right? Whenever that accident happens, the two vehicles are moving in different directions. Now what happens is, this particular molecule changes its path. right? It goes and strikes another molecule here. And when it strikes another molecule here, again, it has to change its path, or the path gets changed, I can say. And it goes and strikes another third molecule. Then again, it changes its path, travels in a different direction, strikes with somebody else, travels in a different direction, strikes with somebody else, again travels in a different direction, strikes with somebody else, and so on and so forth, right? Now, this is the collision between two particles. I'm talking about one particular particle, and this particle is going on colliding with different fellows. Now, what we are going to talk about, we are interested in a quantity which I call as the mean free path. Now, what do I mean by free path? Free path means the molecule is here at this place, and there is another molecule here. So this molecule is going and striking this fellow, right? So this distance that it travels between a collision, right? The straight line path that molecule travels between a collision, right? Between two collisions, that particular straight line path, I call it as the free path, right? And if I'm talking about a molecule, this molecule, they are having Brownian motion, they are moving at random. So I'm interested in a quantity called as the mean free path. Now, what is the mean free path? It is the average distance traveled by a molecule with constant velocity between two successive collisions, right? What is the mean free path? The average distance traveled by the molecule with constant velocity between two successive collisions. Now here, what am I going to consider? That the particle, say for example, this particular particle goes and strikes in this particular region. Let me say this path is say 2 centimeter, then 3 centimeter, 4 centimeter, 5 centimeter, 1 centimeter, and so on, right? I add up and divide it by the number of collisions, and that is going to give me the mean free path. Now this mean free path, let me talk about this mean free path. How does it is not going to be constant always. It is going to depend upon the density of the gas, right? The more the density, the lesser the mean free path. That is, between two successive collisions, it is going to travel a very small distance, right? It is going to travel. Somebody's mic is not on mute state. Please, students, mic. Okay, right. So it is going to travel a very small distance if the density is large, right? Mean free path is going to be it is inversely proportional with the density of the gas. That is, more the density, less the mean free path. More the density, less the mean free path, right? Higher the density, more will be the collisions, right? And more collisions, that is why the mean free path is going to be smaller. Now, this mean free path is also related to the size of the molecule, right? The larger the size, the smaller the mean free path, because a big sized particle you are seeing here, and another big sized particle is there. This particle going and striking, the distance is going to be small because of the size of this molecule. And it is not inversely proportional to the size of the molecule. It is inversely proportional to the square of that size of the molecule. Now, how do I write down the mean free path? It is given, it is related to your density, and it is related to the size of the molecule, right? It is inversely related to d square, and it is inversely related to the density, that is rho. So if I put this down, this is your proportionality constant, size of molecule. When I say size of molecule, this d is nothing but the diameter that I have considered. So we are going to have it as root 2 pi d square n by v, right? This is the formula for your mean free path. Let me move on to the next slide. Okay. Now, if the pressure of an ideal gas is decreased by 10% isothermally. Now, what is isothermally? Then its volume will be, I want to find out the answer. What is isothermally in the first case? Isothermally means the temperature is going to remain constant. Isothermally indicates the temperature is going to be constant. Now, what is the answer? I'm going to look into the formula. PV is equal to P1V1, because the temperature is constant, PV is constant, right? Temperature is constant, P volume is inversely proportional to pressure, is what Boyle's law had said. So I can say PV is equal to constant when the temperature is constant, or I have PV is equal to P1V1 at some different stage, right? Okay. Now, what is P1? What they have said, if the pressure of an ideal gas is decreased by 10%, original pressure was P, now the pressure is P1. What is P1? P1 is the decrease in the initial pressure by 10%. So it is going to be P minus 10 by 100 into P. That is nothing but 9 by 10 P. Okay. Now if I put this, then what is the volume, right? If I put this 9 by 10 P, I can cancel off, and the volume is going to be 10 by 9 times the original volume. What is 10 by 9 times? It is 11.11 of V. If I am talking in terms of 100, then in terms of percentage, it is increased by 11.11%. So your answer comes out to be D, that is the increase by 11.11%. Let me move on to the next slide. Now here I am going to, next slide, in the next further we are going to derive an expression for the pressure that is acting on the walls of the container in which you have kept the gas, right? So for that, if I want to find out pressure, force per unit area is a formula for pressure. How do I find out force? It is the rate of change of momentum, or the change in momentum upon time. Or what is momentum? Momentum is mass into velocity. I'm going to use all this in deriving the expression for pressure. Now let me talk about one more thing. This particle is having a motion in one dimension, right? It is a two-dimensional motion. The particle is moving along the XY plane, two-dimensional motion. And here we are talking about the particle is moving. When the particle is moving, it is moving, if it is moving parallel to your x-axis, going and striking and returning back, right? It is going and striking this wall, say, and coming back. So what happens is the Vx, the value of this velocity, the magnitude, we are going to assume that it is same, and the direction is just changing, right? The direction is just changing. But if I'm talking about the y component of the velocity, I'm talking about the motion of the particle in two dimensions, right? And the particle is moving parallel to your x-axis, then it is the Vy component does not change even in direction. Magnitude, so we have said that we are going to talk about constant magnitude. Ideal situation, we are talking about only the direction of the velocity is changing. I need this in the next, when I'm deriving an expression for pressure. Now here we have a container, and the container is having n moles of an ideal gas. Ideal gas, you know, intermolecular forces are not there, right? So no intermolecular forces of attraction there. N moles of an ideal gas are there in this container. This container has, it is a cube, so it has length capital L, breadth capital L, and height capital L, or it has a volume of L cube. The molecules are colliding with each other, and they are Brownian motion, they are moving, colliding with each other, and when they are colliding with each other, they are also colliding with the wall of the container. They are colliding with each other and with the walls of the container. Here I'm going to assume a little, make a little bit more of assumption. I'm not going to talk about collisions with each other. I'm going to consider a molecule, right? And I'm going to talk about that a molecule, and what we are going to do is the molecule is moving, is having some velocity v, and this molecule is having velocity v, and it has some components along the x, y, and z axis. Vx is the component along x axis, Vy is the component along y axis, and Vz is the component along z axis. Now this fellow is moving from, it is moving in this parallel to your x axis, or it is moving in the YZ plane, right? Now here, what we are going to, in the earlier slide, I told you that when it is moving parallel to the x-axis, or it is moving in this particular plane, then it is going and striking this shaded wall, right? Now in this particular shaded wall, when it's going and striking this shaded wall, it is moving parallel to this particular YZ plane, right? Perpendicular to this particular YZ plane, and it is going and striking this wall. Now I know then when it is moving to parallel to this XY plane, right, in this particular region, when it is moving parallel, its X component is only, the velocity value is only going to get reversed, right? It is moving, going and striking the wall. But the Y and the Z component are not going to change, right? So here I'm basically going to do it for X component, and then similarly we are going to apply, it gets applied for the Y component as well as the Z component. Now it is moving parallel to your X axis, your X component, the Vx velocity, with Vx velocity, it goes and strikes this wall. Now when it strikes this wall, what is going to happen? Collision is going to occur, and it is going to turn back, right? It is going to turn back. Now when it goes and strikes this wall, it has some mass m and it has a velocity vx. So its momentum is going to be mvx. Then it goes and strikes the wall and turns back, right? So when it turns back, its velocity becomes minus vx. The mass is going to remain as m, right? So the final momentum after it has strike the wall, what is the momentum? The momentum is minus vx. And initially, what was its momentum? Its momentum was plus mvx, right? So what is the change in momentum that has happened? It is final momentum minus initial momentum, that is minus mvx minus of mvx. This is the initial momentum, and this is nothing but minus 2mvx. Now this is the momentum of the particle that is traveling, right? So this the momentum that is transferred to the wall during the collision. What is that momentum? It is plus 2mvx, right? Momentum that is transferred to the wall is plus 2mvx. Now I'm going to talk about this particular thing, that is what is the force that is exerted by that molecule, right? It is what is that force exerted? I told you in the earlier slide, I gave you the formula. It is nothing but the rate of change of momentum during that particular one collision, right? Okay, now here I know that is we are going to talk about the average rate of change of momentum, right? It is not one single molecule. There are thousands and thousands of molecules that are there inside. So when the molecule goes and strikes, it travels a distance L. When it goes back, and it is going to strike this wall now, right? So again it travels a distance L, right? So this is one collision, this is another collision. Between two successive collisions, what is the distance it has traveled? It has traveled a distance L from this place to this place. Then from the shaded wall back to this wall, it has traveled another distance L. So the molecule has traveled a distance 2L between the two collisions. Let me say the time between the two collisions is delta t. Then I can write down the velocity as distance upon time, right? Or I can write down the time as distance upon the component of velocity vx. So what is the average force? Average force is rate of change of momentum, that is momentum 2mvx. Now here I'm getting into a detailed concept, right? I know that there are n number of particles. I'm going to talk about the velocity of the first particle as vx1, velocity of the second particle as vx2. I have n particles, right? So if I'm talking about the first particle, only one particle, what is the momentum? What is the force? It is 2mvx1 upon 2L divided by Vx1. What is this? This is the time, right? This is the time. Now, this was generally for all the particles traveling parallel to your x-axis or the xy plane. Now, I have differentiated them as particle 1, particle 2. We have n particles, right? So, it is going to be, if you do rearrangement, mvx1 square by L. Now, if I'm talking about the total n, all n molecules, what is the total force? Total force is going to be addition of the forces of the first particle, second particle, third particle, fourth particle, so on, out of which your m upon L is a constant. So we have just taken the remaining things in the bracket, vx1 square plus vx2 square plus vx3 square plus vn square, and so on, right? Let me move on to the next slide. Okay, so what is the pressure? It is average force upon the area of the shaded wall. So average force area of the of that wall is L square. So I get m upon L cube, and this m vx1 square, x2 square, x3 square, xn square, right? Now we are going to talk about this average, right? Vx1 square, x2 square. I'm going to take an average of this, and I call that average of the square of the x components of the particles. How do I denote it? I denote it by Vx square with a bar sign. That bar sign indicates the average. Now, how do I write down the average? Addition of all these velocities divided by the number of molecules, right? So I can write, instead of this bracket, I can write n into Vx square. I can write it as n into the average of the squares of the velocities, right? So I can put this value. Now we know that the particle it is not only the movement along the x-axis or in the xy plane. You have Vy velocity, Vz velocity. If I add this up, you have all these three components. You have the average of the squares of velocities along all the three, right? It is a three-dimensional motion, right? So the by symmetry, we are just going to assume that particles, the velocity along x, y, z, right? The square average of the squares of the velocity is same, or I'm going to say it to be v square bar, right? So, and 1/3 because vx x square plus y square plus vz square. So I'm going to use this concept. And now here what we have done is n into small m into capital N, right, divided by the velocity v. And instead of this particular component, if we add up all the pressure along, this is the pressure along the x-axis, similarly y-axis, similarly z-axis. If I add up all the pressure, this is the formula for the pressure that I'm going to get. Very important, 1/3 n into small m v square bar divided by the volume. Right? This is the average pressure exerted by the gas in the container of any shape. Now let me talk about this one more concept, and that is nothing but the root mean square velocity. That is nothing but the root mean square velocity, right? Now what is the root mean square velocity? What we are going to consider this velocity v square bar, and if I put this value over here, right, and it is going to be 3 PV, I take this 3 PV upon m into n. And I know PV is nRT. If I put this value, right, then that V square bar, that is the root mean square velocity, right? I'm going to take the square root of this afterwards. This is the mean square velocity. At this moment, the mean square velocity is 3 nRT upon, 3 nRT upon n into m. Now, instead of n, I'm going to put capital N into the Avogadro's number. N and n will get cancelled, 3 RT upon m into Na. And if I take the square root, I call it as the root mean square velocity. And the maximum value of that is 3 RT upon m into Na. And I told you what is m into Na. It is nothing but your molar mass. M is the mass of one particular molecule. Na is the Avogadro's number. And this is the RMS velocity or root mean square velocity or root mean square speed of the molecules of the estimated value of for the real gases. Let me move on to the next slide. It is talking about we are talking about this particular calculate the ratio of the root mean square speeds of gases at 30 and 70 degree Kelvin. Now you know that the root mean square velocity is 3 RT by m. So 3 R and m are all constant. So your root mean square velocity is related to the square root of the temperature. So if I put this value, right, if I put the values of the temperature, it comes out to be 1/1:2. At what temperature will the average will the molecule have RMS speed as helium at STP? Okay. Now the molecular masses of oxygen, at what temperature will oxygen molecule have RMS speed as helium molecule at STP? Molecular masses of oxygen and helium are given. You know how you get this 32, 16. Oxygen molecule means O2, O2 means 16, 16 to the 32, and helium means 2, 4, right? One particular helium molecule means He, He42. So 4 is the molecular mass, right? Now this, it is related to the root mean square velocity is under root of 3 RT by capital M. That is the molecular mass. Now 3R is a constant, so it is going to be related to the temperature and the molecular mass, right? So if it is related for oxygen, if I write, it is T1/32, and for helium, if I write, it is STP. Helium is at STP, that is standard temperature and pressure. That is nothing but your 273 degrees, right? Okay. So you have the they are saying that the velocity is same, right? Okay. So we are going to take this ratio, and if we take the ratio, I'm going to have this expression. Okay. So this is STP. I hope all of you all know STP chemistry. You do it n number of times, standard temperature and pressure, and that is nothing but 273, right? So if I find out this answer, squaring, if I square up both the sides, and if I get the answer, this is what I get. It is 2184 Kelvin, right? This is what I get, 2184 Kelvin. One more example is a gas in a cylinder is at pressure P. If the masses of the gas, the molecules are made of 1/3 of their original value, then their speeds are doubled. Now, what I want you to do here is you are going to get into numerical number 13 and try to solve it. I'm just flicking it very fast, right? Okay. So I want you all to get into this numerical number 13 and just go through it. Okay. Now this is all that I'm going to teach you for today, right? So just try to, a gas in a cylinder is at a pressure P if the masses of all the molecules are made 1/3 of their original volume and their speeds are doubled, then then find the resultant pressure, right? Okay. What is happening? The masses are made 1/3 and the velocity is doubled. Okay. So the pressure expression is 1/3 N by V M into V square, right? This is, okay. So if I put the values, I'm going to get this expression, and this is what I will get the answer. Okay. So this some solving is done and this is what you get. And what happens to the pressure? It is 4/3 times of the original pressure. Okay. Now, right. This is all. Anybody has any kinds of doubts? I hope all of you all have given your attendance in the attendance sheet, right? Okay. Anybody has doubts? For today, we are going to stop here with this particular thing. I want you all to do some homework, and very important, today evening only I want a photo of whatever you have done. Please write down your homework. Question number one, you are going to write down the ideal gas equation in terms of your gas constant R and also in terms of the Boltzmann constant. Am I clear? Ideal gas equation, right? In terms of Boltzmann constant and in terms of your capital R, which you already know PV is equal to nRT, but I want you to write it in terms of Boltzmann constant. I need it in the next class, right? Then second question, you are going to write down. Am I clear with the first question? Now the second question is, you are going to define the mean free path. The second question is define mean free path, right? Then and write down its formula also. Define mean free path and write its formula. The third question is very important. It is a 3 marks question. You are going to derive the pressure of an ideal gas, right? Am I clear? You are going to derive an expression for the pressure of an ideal gas, right? Derive an expression for pressure of an ideal gas. And the last question is show that the RMS velocity or RMS speed of the molecule of a gas is directly proportional to square root of temperature, right? RMS speed is directly proportional to square root of temperature. This is 4 questions I have given. First is you have to write down the expression for ideal gas equation. Second, you have to write down the definition of mean free path, right, with its formula. Third question is a big question, 3 marks question. That is, you are going to derive an expression for pressure of ideal gas. And the last question, you are going to show that the root mean square